Hello everyone. It's April 2nd. Alright, let's get to it. Maximum value of a order triple. We did the first one, right? That was yesterday. Yesterday was the first one. This is the second one. Zero indexed, and the maximum value over all triplets. The value of a triplet in the CC is I minus j times. Huh? Is it not the same as yesterday? Oh, dude, that's exactly the same problem. Exact same problem. They just oh yeah, exact same problem. They just made a little bit change to the to the constraints. All right, what code it again? All right, we'll code it again. It's prefix suffix, right? We'll do a prefix suffix thing. And in fact, we only need a suffix because the prefix we can just keep using it. Right? If you think about it, the prefix we can keep using it. We don't even have to create a prefix array. We just need to create a suffix array. Yeah. So still, I mean, a little bit improvement from yesterday. Right, so basically, we'll have so this is exactly the same as problem 2873, except that the constraint is stronger with much longer nums. We'll use the prefix and suffix max. Alright, we do need a vector of int suff max. Alright, so for int I, we shall do suff max n minus 1 equals nums n minus 1. Right. And then this should be n minus 2. And with a suff max I shall equal to maximum suff max I plus 1 nums I. Okay. So, and then we have premax, right? Premax should be nums 0. Okay. And then we say long rest. Then we say for int I equal to 1, I smaller than smaller equal to n minus 2, because that's the last one I can get. I plus plus. Say rest shall equal to max rest. Alright, so what we're gonna do is premax minus nums I times suff max I plus 1. But every step we have to turn this into long. And we'll return rest at the end. Oh, I forgot to update. Yeah, it was my bad. I forgot I need to update. Premax shall equal to maximum premax and numSci. Don't forget premax. Okay, we got today 6 milliseconds, 47. Yeah, really there's nothing to say. It's exactly the same. Alright, so we done with this. We'll probably try this one again. Yeah, let's cancel this. I remember this. There is a road between intersection. You want to know how many ways you can travel from intersection 0 to intersection -1 in the shortest amount of time. So, I remember this is Dijkstra, right? Because Dijkstra can guarantee that when you reach the destination, it's the minimum time, right? So all we need to do is, as we go through Dijkstra, right? Once you go through this to this, you have to keep track of a number of ways, right? A number of ways, like how many different ways you can go. Because if you have, you know, like 2 ways to reach from A to B, and then now you want to go from B to C, then you look at B. B has 2 ways, so that means C will have at least 2 ways to get there, right? So you just keep this up. And every time, how does the number of ways increase? Well, so you go, you know, from 0 to something, you say I have 1 way, and then from that going down, you have like whatever number of ways, and then you'll have somebody else might come to you, and when they come to you, they will be bringing more ways. We can actually try it with this example. So if we have a count the number of ways, okay, so we have 6. Right, I drew too much. This one doesn't count. All right, so from 0, everybody start from 0. 0 steps, 0 ways. So first we go to 1. So 1 have 1 way. Actually, no. 0 need to count as 1 way. Otherwise it won't work. Sorry, 1, we have 1 way. And then we haven't visited 6 yet, right? So basically we go 1, we go 6, and we go 4, right? We go 1, 6, and 4, and we put it in there, and then 1 pop out. Okay, then we check, and then we add 3 and 2 into it. Now 3 and 2 both are 5, right? So I put in there, this one will probably come up second, so this one will be give me 1, and then this one will have, well, it can go to 0, right? It's fine, it can go back, but usually you visit it, you don't try to visit again, right? The first time you visit is always the cheapest. Oh, no, it's like the cost, right? The cost. I go sick. Yeah, It was safe, so it was 6. So 6 got hit again? No, because I didn't get smaller, so I don't hit 6 again. Or do I? I think you do. I think you do. Because that's like 2 ways, right? So you just put 6 in there, that's it. And then that 3 comes out. Now 3 comes out, we'll look at 1. 1 has a 1, so 3 has a 1. So 3 comes out, we go to 6, which is cost 8, right? And it's bigger, so we don't do that. We don't do that way. 5 I do. So 5 will get 1s, and that's it. And next 2 comes up. All right, so 2 also count as 1. And then we go to 5 as well. Right, because 5. Oh well. Oh, next. So next should be 5 comes out. Right, and remember, there are 2 5s in there. So the first 5 comes out. We'll look at 3. So 5 will get 1 count. Then we'll go to 6. Right? And then 5 comes up again. And then we'll add this one. So now 5 gets 2 count. Right? And then we go to 6. So finally 6 comes out. So we basically have 1 from here. Right? So come from 4. And then 1 from 0. So we have 2. And then we have 1 from, then we have 1 from 5. Because 5 also push it in. This will be wrong because 5 will count twice. 5 already 2, so we become 4, becomes 6. So this doesn't work. So each node should only be visited once. But if we have a path going there, we can update. So 5 will get 2 ways, but we're only gonna push it once. So like if it's smaller, then we do this. If it's equal, we just update the count, but we don't do that. Yeah, we have smaller equal to, we do that. And if it's smaller, then we will also push. Okay, so that's kind of how we're gonna do it. And you wanna do the C++ again? I actually think we should. We really should, because I'm doing I'm doing Python every day these days, and then very soon I have to do C++. I mean, these I don't really know if they really help or not, but I'm not sure if they help. At least have some muscle memory. It's better than nothing. Alright, so we're gonna do it again. We need a queue. A priority queue. Okay. And this priority queue, what will it store? The priority queue will store I forgot how to set up priority queue. Two things, right? It has to be a pair. Right, it has to be a pair. I remember. I try not to do it. I just try to, we do pair. We do int. Alright, so this is a queue. Right? Now it's a queue. Ooh, but before we do that, we need we have n. Alright. We have n. We need a vector of int graph auto const e of rows three values. Oh, cannot be. Has to be a pair as well, right? So it's a graph e0 dot pushback e1 e2, right? It's time is the second one. Okay, okay, so this is to set up. Oh, hold a second, I need n. All right, so this is to set up the graph. In one shot. All right, so now we have the Q, and then we'll say Q dot push. So we'll do each element is cost, right? Cost and node. Well, we want to find a minimum, but this is a max Q, so we have to go like reverse. Oh, one more thing we haven't done. Vector int was this. This is going to be the min costs. Oh, I set the largest. Now we can just do int max. Can we do int max? I thought I can do integer max. It doesn't have it. Huh. I have long max. There we go. All right, and then cost, minimum cost, right? Minimum cost is 0 shall equal to 0, and this is going to be cost, and the node is also 0. Okay, now what? One more thing. Num ways. That's just 0. And num ways 0 need to be 1 because you only have one way to hit there, right? Okay, while q dot empty, of course we want it to not be empty, and no, there's no and, just like while q is not empty. We say auto p shall equal to q dot top, right, and then q dot pop. And we have the current cost shall be minus p dot first, and current node is p dot second. All right. So that's when you visit it, right? But we don't really do anything about it. We're gonna go check its children, right? So auto C child of graph node, right? So it's really our child. It's called PP. Okay. So in child shall equal to PP0, right? And then C shall equal to 1. This is the cost, right? And we say if here's the key. If cost is the current cost plus C, right? The smaller equal to min costs child. Right, so we come in here. So the first thing we do is we need to num ways child, right, plus equal to num ways node, right? Because you come in here, you just say we'll go there, so we keep track, right? And then we need to make sure we only push once, right? We only push it once, and we say if cost C is really smaller than costs child, right? So it's really like even smaller. That's when we say q dot push, right? When I push negative cost minus C, right? Mind you, we have to go negative, and then child, and we can say min costs child shall equal to cost plus C, right? We update the min cost on the child. So we keep going. Alright, we keep going, and then we just return min costs n minus 1. Let's see if it's correct. We trying to one-shot this thing, but that is not good. Output 7. Oh, that was rough. 10. Oh, that was rough. Okay, so maybe I also need to do here. So basically we say if cost node, if cost is larger or equal to, all right, larger or equal to min costs node, then we'll continue. I'm not sure if this is how we can make it work. It doesn't really make it work. I do have the mod, but I don't think we're there yet. I have no idea. I think once you don't have an idea, we might need to debug this. We can like a simple debug, right? We'll just kind of check what the costs and the nodes are. Now we just cost and node. Well, just run it and then see what it come out. Oh, look, I got 0 and a 0, and then we'll have nothing. We have nothing. Oh, I think I got this one wrong. Cost should be 1 when we start. Okay. -1, my bad. What happened? Cost is 1. Node is 0. Oh, main cost should be 1. Oh, wait, hold a second. The cost then is a different thing. Weight is 1. Cost is 0. Cost is 0. I got confused on these two. Alright, we'll try it again. Cost is 0. Number of weights is 1. Yeah, cost is 0. And we are checking cost. If it's larger or equal to, which means equal to, then I don't do it. Now, apparently that's not correct. I should just say if it's larger than, then we don't do it. Right? Equal, we shall do it. Okay, equal, we shall do it. All right, still not right. But we go through a lot. So we start from 0 is 0 cost. And then we have 2. 2. Cost is 2. Yeah, cost is 2. We go to 1. And then cost is 5. We go to 4. Cost 5. We go to 3. Cost 5. We go to 2. Cost 6. We go to 5. and cos 7, we go to 6. Exactly. All right, so the logic is good in terms of this, but I think our num ways, I think it's not right. But I don't understand why the num ways does not make it correct. So because my num ways only add the child's num way, or plus equal to the parent, right? Plus equal to the parent num way. And all I see is 1. Right? This should be the first 2. I don't understand. Oh, because I return mean costs. That's why it's wrong. It should be num ways. See, I was saying that I got confused with these two. We have a kind of 2 arrays going on at the same time, and then it really, bothers me. This, I think, looks very promising. Oh, but we got wrong. Okay, there are 2 things here. First, I did not mod, so I probably need to mod as well. Second, is it just the logic was not right? Do. I don't know. We have 0, 1, 5, 0, 2, we have 1, 1, 3, we have 1, 1, 5, we have 1, 2, 3, we have 2, 2, 4, we have 1, and then 3, 4, we have 1. Let's use this test case. 6 nodes, not too bad. We do have to, let's also add a mod here. So int 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what we do is every time we do this, shall equal to num ways child plus this mod, and let's do this. Same thing. Cost. Right, so 0, then go to 2, it costs 1, then go to 4, costs 2, go to 3, 2, 3 costs us 2. Okay, so it's a little bit confusing. Let me rearrange this. So 1 to 5 costs is 1. Yeah, so come to 3 costs 3, and then come to 1 costs 4, come to 5. That looks about right. So 0 to 2 cost 1, and 2 to 4 cost 2, and 2 to 3 is cost 3. Oh, hold on. I think once you find something small, you have to reset the clock. That must be it. I did not reset the clock. So basically, right? I see. So if it's smaller, then num weighs child shall equal to num weighs node. And then min costs child equal to cost plus c q dot push negative min costs child, right? Else if cost plus c is equal to min costs child. This is a tricky one. Then we do that, don't do this, and don't do this. Okay, let's try this one more time. Yeah, now we are good. Let's also reset all the test cases. And let's get this one as well. Run it one more time. Just make sure that everything works as intended. Now we can submit. Yeah, there's a little bit logic here. Ooh. Okay. That's okay. That's, you know, we expected that. So that just means this has to be long, right? Because you have to compare. You cannot compare based on, so this has to be long. Yeah, that's okay. I do long. So this should be long, right? And then blah blah blah. Cost is fine. This is all fine. So cost is an int, which is not right. Cost is a long. Node is an int. Right. Node. Oh. Node is an int. And then cost plus c. What the hell is c? Okay, c, let's long it. Min cost. Min cost. Let's get min cost also. Let's make it into long. Yeah, I only have long max. It's fine. So min cost. Right. And c is that. C is long. Cost is long. So long plus long smaller equal to smaller than this. This and this. This is long. All right, so we hit some long here. Long, man. All right, let's use this test case. Try it. not sure why you have this one open. It doesn't make any sense. All right, let's submit again. Put some long there, and now we got it. Pretty neat, huh? Pretty neat. This one's pretty neat. Yeah, I mean, we already know how to solve it. But just more practice. That's essentially what it is. Did we get 0? We got 7 last time, but I think the aren't we doing exactly the same? Well, we put long here. That's a difference. The other looks about the same. Do that. We 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 do that. Do that. Do that. Oh, meantime, yeah, it looks about the same. I don't know. It just. But anyway, now we can close it. That's all we want. We solve it one more time, then we can close it.